we'll have, Hugh will go through his slides, and then each of the panelists have a quick introduction on where they've used open source in the past for research, what they're currently working on in the research community with open source, and what they need from the ecosystem. And then after they all go through those slides, we'll open it up to generic Q&A and see what kind of projects we'll be able to brainstorm on to foster more collaboration. So where you go, Hugh?
Thanks. Okay, so as Rick mentioned, my name is Hugh Pollitt-Smith. I'm from an organization called CMC Microsystems. And we have a panel of 6 researchers from across the country. Before we get to the actual panel, I'll just introduce CMC Microsystems and how we support universities doing microsystems design in Canada. So CMC is Canadian Microelectronics Corporation. Or CMC Microsystems, we've been around since 1984, and we manage what we call the Canada's National Design Network, and we deliver micro-nano innovation capabilities across Canada, and this includes embedded systems, microelectronics, photonics, MEMS, microfluidics, packaging, and test of those devices. We deliver products and services in 3 broad categories. One's called CAD, which is fairly self-explanatory in terms of CAD tools. We offer a number of tools and design environments for designing those microsystems components and systems. We make them available on researchers' desktops as well as in the cloud. We also provide user guides, training, application notes, and do courses to learn how to use the tools most effectively. Following on from CAD, we offer access to device fabrication. We provide multi-project wafer services with affordable access to foundries worldwide. We also provide packaging and assembly services, and also in-house technical support and consultation to make sure that devices work. And then we provide services in the lab in terms of test equipment that are available for short-term loans so that researchers can test their devices when they get back from fabrication. We also do contract engineering services and develop custom technologies for researchers, startups, other companies to create infrastructure that can be used by others. As Rick mentioned, we support 67 universities and colleges across Canada and 10,000 academic participants and 1,000 companies with whom they collaborate in designing, making, and testing microsystems prototypes. And we call this Canada's National Design Network. So annually, we work with over 1,200 professors and their research teams. We have over 6,000 users of the CAD tools that we provide, and we see 300. At least last year, we saw 360 prototypes developed by those researchers, and the test equipment that is used. And in terms of how we measure our success, we measure our success through the outcomes of the researchers, so the publications they make, the awards they receive, the patents that get awarded, the startups that are created, and the HQP that moves to industry in Canada. We provide these services by engaging with suppliers across the country, around the world. So this could be suppliers of CAD tools, fabrication, nanofabrication services, university labs, system and component companies, packaging companies. So in terms of how CMC sees itself in sort of this RISC-V movement, CMC for researchers, startups can provide a path to implementation, whether this be FPGA implementation or ASIC. We could provide silicon-proven design platforms, the CAD tools and flows for virtual prototyping, FPGA prototyping, emulation, ASIC implementation, PCB design. The embedded software toolchain and the entire software stack to make these systems operational. FPGA platforms for emulation and validation, design kits, IP for fabrication and commercial technologies, multi-project wafer fabrication services, the packaging and assembly, the test equipment, access to a demonstration board so that custom prototypes can be quickly and easily integrated onto something that can then demonstrate the research, and then provide engineering support and consulting and design services around these platforms. One example we've thought about or looked at is I guess a question is there a sort of a common RISC-V platform that researchers can customize by developing their own accelerators specific to their research, and then in sort of a multi-project wafer fashion, fabricate a number of devices with several of these accelerators, and then that sort of aggregates the cost of fabricating these large system devices. And those can be proven in an emulation environment, and then eventually go to ASIC and be put onto a demonstration board. Another technology we provide that could be of interest in the RISC-V area is a cloud-based remote access FPGA GPU cluster that's just been installed at University of Waterloo at their computing facility. And this is a cluster of 8 nodes. Some of the nodes have multiple GPUs, some have multiple FPGAs, and some have a combination of FPGA and GPU. And these can be used for developing machine learning, training and inference, acceleration, video processing, financial computing, other sorts of high performance computing applications, and then also to develop and prove RISC-V accelerators for open source cloud computing. And in addition to the hardware that's provided, we also provide a complete software stack for the cluster based on Dockers, which are created for specific frameworks or software applications, and then these run on top of the underlying hardware. So these are available now, and my colleague Yassine Hariri here, if you have any questions on how to access this cluster, you can certainly ask him later on. So that's a brief introduction to CMC and our interest in RISC-V. And so now we'll turn to the panel, and the format of the panel, the order of the panel is the order I received slides, so just so you know. And the format would be that each panelist will present a few slides, as Rick said, sort of describing what they've done with open source hardware and software in the past, what they're doing now, and what they need out of the ecosystem and the open source community to further the research. So first up is Michael Fiorentino from Polytechnique Montreal.
Thank you. So yeah, I guess I'll start. So I'm Michael from Polytechnique Montreal. I'm still a PhD student, but I worked a lot with RISC-V and in research and in teaching, because I have a lab on VLSI design and we do a microprocessor. So I'll go with that. I changed a bit what Rick asked, sorry. I'll talk about what we do in research, what we do in teaching, and then what we would love from the community and from what would be cool to have as open source hardware. So I'll start with what we do in research. We use RISC-V because we started a project on asynchronous processors, and well, at the beginning of the project, which instruction set are we going to use, and that were the time where RISC-V came around, so we decided to go with it. The main reason is, well, it's open source, so we don't have to wonder about can we use it or can we not. That's the main thing. And the other thing is the modularity, because we can use, as Rick said this morning, we can use any subset we want. So we use just the I and M extension. I mean, the I base and the M extension. I will not go in the detail of the microprocessor, but basically the idea is to explore microarchitectural concepts that can lower the power consumption. And basically this is done through removing some of the consumption from the clocks. That's why we made it asynchronous. And so we designed 2 processors, one asynchronous and one synchronous that is a baseline that we can compare it with. And we did the implementation, I will talk about that later, in 45 nanometer from Cadence. It's not a real ASIC kit. We cannot fabricate with that. It's just a kit to do simulation, but the advantage is completely open and it works with all their tools, which is sometimes not the case with some other kits. But we also did it in 65 nanometer from TSMC, which this one can be fabricated. So that was from the research perspective. And from the teaching perspective, we've been doing actually 2 labs. The first one is a MIPS, of course, and the second one is a RISC-V, and it's just a textbook RISC-V. Because it's not a computer architecture course per se, we have removed some of the instructions, so we use just 25 instructions, but still we use the RISC-V toolchain. Just we make sure that we don't add instruction that we don't support when we compile our benchmarks, and that's it. So the students, they have to design that from scratch. We just give them the specification that is adapted. First, it's in French because it's in Polytechnique Montreal. And second is because it's adapted, it's the same opcodes, but just we have removed some instructions. So they do that, they do their 5 stages pipeline, they do basic branch instruction, basic memory, and then they have to go through the whole design flow of the ASIC, just an introduction, but still they go through all of that. They use all the proprietary tools that we use in the industry. I mean, not all of them, but the one we choose. So Cadence tool and Mentor tools, we used to use Synopsys tool, but we stopped for some reason. So yeah, that's basically it. So 1 year they do RISC-V, the other year they do MIPS. That's to avoid the cheating and stuff like that. And I didn't mention, but both of it are available on the GitLab. And I use the GitLab that is provided by CMC. So CMC provide a bunch of tools. So for both research and for teaching, I put that here. The reason is mainly the NDA that we sign, because we sign NDA with the kid. We sign NDA with the layout of the cell. And this, we cannot really put that on GitHub or somewhere. We have to put it somewhere we trust or else. I mean, we could do it, but then we would be breaking the NDA. So this is very useful for that. Although I encourage more people from the research in Canada to use it because there's not much people there. Anyway, so then the question is what can we improve or what could be good to have in the open source ecosystem for hardware? So it's a mix of a lot of things. First thing is with CMC, I don't know if many of you have worked in a university in hardware, but if you did, you work with CMC. And with CMC, they provide all the tools for us. But this is missing. We still don't have the RISC-V tools set up properly. So I guess this will be done soon, I'm sure. That would be great to have so that we don't need to go through all the configuration. We could do it. It's good to learn, but then we spend a lot of time learning stuff in research and doing PhDs and stuff. So this can be good. Now, the main thing I think can be useful for us as researcher is verification. So as the talk of this morning was very, very interesting. Why, especially, I mean, it's true for any kind of industry, but in research, what we produce is papers, basically. We don't need something that can work. We just need a proof of concept. So we will never work on verification, except if we are researchers on verification. So basically, working on verification is a waste of time for a research perspective. You just, if your benchmark is working, that's it. You don't need to worry about anything else. But that's not good, right? So if we had verification IP that we could use, ready to use, and we don't waste time with that, that would be great. Then with the same idea is we could, depending on what we do, if I do work on microarchitecture, so I will not reuse maybe code that's been designed for another core, but if I work at a higher level of abstraction, I could use work that we have done. So we should have a better user base of IP cores and FIFOs and bus and a lot of, so I know there are projects starting, but compared to the software community, the hardware is very lacking in open source stuff. Then we need benchmarks for two reasons. We need, the main reason is we need something to compare what we do in research with something standard. And we don't really have that right now. For example, in processor design, that's what I know best. We design our processor, and then it's like, okay, with who are we comparing with? So, are we comparing with ARM? They have an army of designer, and they have their chip at 7 nanometer. We're not comparing with that. We cannot win. So there is no way. So we need something, some standards. So maybe the risky processor can be that standard. And also we need a standard in terms of which technology this processor is implemented on. So I don't know, the Cadence kit that is not something to be fabricated can be used because it's provided to everyone that use Cadence. But I don't know if you have any idea, whatever you think. Maybe an open source kit, an open source ASIC kit can be developed. I don't know by who, but that would be great at some point to have that for the same reason, having something standard. And then the obvious, what can be, we could have more events like that. I think it's very, very good to have to meet people and to train. And collaboration. I think CMC at the research at the university level is good. They provide Git. I give here two examples what that stuff they could use, cloud and the communication like Slack kind of thing. So that's it. If you have questions, see you later. Thank you.
Hi, my name is Miodrag Bolic from the University of Ottawa. So I do research in computer architecture, biomedical engineering, and AI. So here I'm going to talk about open source in teaching, not in research. So first, why open source in teaching? So we can use different tools to reduce the cost and to increase the engagement of our students. Students get really excited when they work on open source and contribute to the community. So what we use at the university is software. We use open source hardware like open hardware boards, simulators, OSs, and we use, of course, instruction set architecture. Open source. So this is a course that I was teaching in 2018 on computer architecture. So we were designing the RISC-V processor using BlueSpec. So the students had to do the labs. So they started with a basic core, and then they added pipeline stages. They added caches and so on. So this course was based on course by Professor Arvind from MIT, and so my experience in this course was that we had a lot of problems with the tools, and students got stuck pretty often. And we got great support from MIT, from people involved in that project. But still, we had more problems than help. So what would be really great if there is some kind of training organized, especially for graduate students, so that they can get more experience with the tools and with RISC-V, and then they can help and teach undergraduate students in the lab. So besides this, I was using also other open source tools, like, for example, open source simulators, for example, from academia, like Multi2Sim for design space exploration. So the students were kind of designing their own GPUs in simulators and CPUs and running the code on it. Again, great tool, but developed by academia and no support. And whenever we get stuck, we are really stuck. So this was the problem. Also, we were using kind of inexpensive open hardware boards like this Parallella board with the 2 arms and 16 core accelerators. A great concept, again, issue with support. On the other side, when I teach machine learning courses, everything is open source, all the software is open source, but it's really easy to use it. There is a great support from the community there. So it will be great if you can have something like this with RISC-V as well. Okay, thanks.
Hi, I'm Sebastian Magarovsky from York University, Electrical Engineering and Computer Science. I'm the faculty there. So as far as what we've done in the past, that's mostly revolved around FPGA acceleration, and it's specifically focused on embedded bioinformatics. So one of the pictures has cut out there, but it's the state of technology. Certain aspects of the technology have gotten to the point where you can do some bioinformatics in small handheld devices, which makes the opportunity or opens the opportunity for custom circuits to be implemented alongside those to accelerate some of those computations. So that's the research, and the open source aspect of that work has largely just been on the interface front for us. So on the right side there is the interface framework that we use for that work, and that's RIFA, the Reusable Integration Framework for FPGA accelerators. So we've got an FPGA and a PCIe slot running a kernel, and the CPU has got the rest of the bioinformatics program on it, and then they're communicating in a streaming fashion to solve a problem, some kind of a streaming problem in the bioinformatics pipeline. And it provides a very convenient interface to use, and so I think it's a very great example of how successful and sufficiently documented an open source project could be. And what we're doing now is more of the same, but with an emphasis on porting the work that we've achieved in FPGA to ASICs, again, on this embedded bioinformatics front. And the open source aspect of that now embraces the RISC-V family. So we want a specialized accelerator in ASIC form on the same die as a RISC-V processor working together. And some of the other open source tools that we have used a little bit in the past and are trying to exploit a lot more focus more from the design productivity perspective. So that would be Chisel, which we've just marginally used, by PyMetal, which looks very promising to us, at least from early experiences. And what's needed from the community, so at least in our case, I/O is a really big deal. So for example, that FPGA project I mentioned, the design we have now, working with PCIe 2.0, which is what RIFA accommodates, is at about 800 megabytes per second. But improvements to the design are very obvious once you've worked on it, so it can easily be boosted up to 3.5 or 4 gigabytes per second. That would be a problem for 2.0, so even a now stale solution like RIFA would need to be updated for the new standard, possibly, and then even for different types of FPGAs or more advanced FPGAs. All our stuff was on the 7 series, so UltraScale Plus could involve other aspects. It would be great if there was some activity from the open source community on that front. And then on the ASIC side, again, the same question about how can we communicate effectively our ASIC with the RISC-V tool. I guess there are protocols, accelerated communication protocols that have been described for RISC-V, but even getting that signal off chip, that would be really handy, and even how to connect that RISC-V accelerator chip, package it on a board and get it connected to maybe a PC, get it booting an operating system if possible, or at least have it operating in some kind of a tethered fashion. All of these things at the periphery are really the most challenging, we find. I think that the ASIC itself, especially if you're not overly worried about the verification front, which you should be, but let's say at the beginning too, if you want to show a very impressive innovations on the architectural front. It's just the ability to demonstrate that working on the board. I think that seems very difficult for us. Thanks.
Hi, I'm Guy Lemieux, and I'm a professor at University of British Columbia. I'm also CEO of a small startup called Vector Blocks. So I'm going to talk to you from both perspectives, sort of combined, both as a professor and as someone who started a small company that tries to build IP as a hardware business model. And it's not been open source IP for the most part, but there is a small piece that is. So let me talk about that. In terms of past IP that I've produced, one of the earliest things that I did in grad school was I made high frequency counters that could count events, and you could add a large number of bits, like make it a 64-bit or a 256-bit or a 4096-bit counter, and it would have the same clock speed no matter how many bits were in there. And it wasn't just a ripple of the clocks or something like that. It was a fully synchronous counter design. And I was pretty proud of that because it was interesting to play with FPGAs at that time. And the standard counters had these slow asynchronous carry chains. Fast forward, I'm a professor. I've got some great graduate students. And so I team up with one of them and I found Vector Blocks. And we took something that we started at the university and we weren't sure if we were going to open source it or not. But we brought it into a company and we said, well, this is hot. We can't open source it because the only thing we can do is license it for money. And if it's open sourced, we're not going to make any money. We wanted to actually have this live and breathe and be used by people. And we thought we had to collect revenue on it to pay our salaries so that we could provide support and get this out there. And so we produced this vector processor called MXP. And then we provided CNN acceleration and DNN acceleration for MXP. I'll talk about the success of that a little bit later, but it's challenging to build IP and sell it. So then RISC-V came out and we said, hey, this is open and everybody's going to have a RISC-V processor. Why don't, as a calling card, we make our version of a RISC-V processor and just put it out there as open source? It won't take us too long. And then that'll bring some business in. So we did that and we made Orca, which is a free open source BSD licensed RISC-V processor. It was one of the earliest processors that was out there, fully pipelined implementation. And unlike most of the others, it's not written in Chisel or based on Rocket. It was a from scratch design, purely written in VHDL. It might be the only 1 or 2 or 3 implementations out there that are written in VHDL. All the rest are in Verilog or in Chisel or something like that. And so that's out there open source, and it did bring in a lot of referrals. A lot of interest for everything came through that. It was a really great decision. But we still didn't have the courage to make our main business, the vector processor, open source. In parallel at the university, I had another great student who was doing some work, and he said, I know what I want to do. I want to do some memory design stuff. And so he built multi-port memories. So you could build 4 write ports and 18 read ports or something like that. And he has a whole bunch of ways of building them in very clever ways so they work at very high speed and they're very efficient on an FPGA. And then he invented some new ways of making switchable ports and saving area that way. And then he took that and he went and he built cams on the FPGA. Now it's really easy to build a small cam on an FPGA, but it's really hard to build a really, really big cam and have it high throughput and low latency. And that's what he did. So you can basically turn all of the memory on the FPGA into a giant cam. And we decided, hey, we're going to make all this open source. And so it's all out there. It's on Git. You can go and check it out. And he wrote huge test benches and everything and put it all out there and made sure it was all working. And there's a few people that have picked this up and used it. And the latest thing is the ability to do ternary cams, which would be used in network IP routers and stuff. What am I doing now? I'm doing more on the university side now than Vector Blocks. And I'm still looking at RISC-V. I think it's a great initiative. I'm looking at building a new type of RISC-V CPU at the university side, and I'm probably going to make that open source. Orca was optimized for FPGAs, and we have it running on every major FPGA family: Lattice, Microsemi, Acronix, Intel, Xilinx, and everything. So it's extremely portable. But I'm going to do something on the university side, and we probably won't have the resources to make that fully portable, but we'll want to. Building the CPU in a new way is a research item, but porting it to all these other implementation platforms is not a research issue. And I don't know how to resource that. I don't know how to get students to spend time on that. I don't know how to pay an engineer to do that because I don't have any money at the university. I want to work with new tools for building systems. So I want to not just have a RISC-V processor, but I want a memory controller. I want a PCIe controller. I want a network controller. I want simple things like a UART and I2C controllers and things like that. Also, I want accelerators for neural nets and other workloads. So I need tools for building these systems together. And there are some tools out there. If you work with Vivado or Quartus, they have tools like SOPC Builder and IPI. But there's no universal tool for all FPGA targets. There's a new one called LightX that's out there that's sort of starting in this direction, and that's an interesting one to look at. I think we need more of those. So I'm going to work a little bit in that space. I'm also looking at building some mini-core arrays and some vision systems based on OpenVX as new IP to come out. So these are in the pipeline. Where do I see some help coming in? Well, this has been documented by some of the previous speakers about we need some more IP, especially hardware modules that we can attach to RISC-V and other things. One of the things I like is a lightweight debug JTAG controller that anyone can use, because you build a processor, it's got a 3-stage pipeline and everything, but then how do you single step it through GDB? Also, the peripheral library, the PCI endpoint has been mentioned, RIFA. That's work. It was great, and it was put out there, but it's not open source for commercial users. It's have to negotiate with UCSD for it, and it doesn't work. One of the first customers we had, they wanted to get some data off a camera link interface and into a PC on Windows, and we tried to use RIFA, and it didn't work with Windows, and we tried to get them to use Linux, and they said no. So we had a lot of trouble with that, and ultimately we ended up sending the data through a UART, believe it or not, because we couldn't get the PCIe to work. But that's all needed, and including scatter gather control for high performance DMA over PCIe. More of the system tools that I referred to, and that includes multi-vendor support across all vendors of FPGAs in particular, and simulation environments for that to work, things like Verilator in order to simulate the hardware designs, and also building the board dev kits. So these are the SDKs that have the header files with the addresses and stub routines for all the device drivers and everything like that, all Laker scripts all put together. All built with open source tools. This is not yet a capability, but it's something we should work towards. I think for open source hardware, if all of these availability things are out there for FPGAs, we can do custom PCB fabrication and make that as easy as FPGA testing. So right now we use FPGA boards that are pre-built. We bash a bunch of bits in there and it works. I think we do the same thing with PCBs. We can basically build the schematic and then essentially outsource it in the cloud. Someone else does the detailed placement and routing of the PCB and manufacturing, and it comes back pre-tested and ready to work. Most of that is in place, but it's not all put together in one easy-to-use solution. You have to shop around a bit and stuff, but I think we can make something totally easy so that people can be very, very novel and inventive on what to do with their hardware. Some of this is research and we can do it at the universities, but some of it just takes engineering support and labor to maintain and port. And some of these things that you've heard about, like RIFA and other things, don't have the engineering support that you need to make these things long-lived and to do the verification and bug fixing. This takes money and time. I know companies can try and work with us and donate some of the money needed. We could also use volunteers in the open source movement to donate some time. And we'd like to have engineers on staff at the university, but we need a regular source of money to help integrate all this and provide this as a service. The last thing is a little bit of a cautionary tale about the success of VectorBlocks, for example. What I learned through VectorBlocks is that selling hardware IP is not a great business model. If you think you're going to make this IP module in hardware and you want to sell it, and you can do it in your basement just like software, it's really hard. You have to actually overcome a lot of challenges. With software, it's really easy. You have things like the Apple App Store. That makes things really easy to distribute and get customers. But with hardware IP, the customers are inherently skeptical. They're not willing to try things because that's going to cost them a lot of money. For you to build the IP, you have escalating costs for verification, support, and marketing, and trying to get your message out. It's really hard to get testimonials and get credibility with your customers. Us joining RISC-V was a really big thing for us, getting both marketing and testimonial results. It's really hard as a small company to get traction with big partners to help you. For example, getting the attention of Altera or Xilinx was virtually impossible because they wouldn't get out of bed for less than $1 million. But for us, $10,000 was a big deal. And every single IP company that I look at actually makes more money on services than they do on licensing the IP. So if you think you're going to make money on licensing IP, just a cautionary tale, be careful. My company fell into that pitfall. So if you can't make money out of licensing IP, maybe you shouldn't bother trying to make money out of it. Maybe you really should make it all open source. That's sort of the message here. And maybe that's true because the licensing isn't a really valid business model. It's not a sustainable one. But you still need to have some income coming in. Something has to give there. And part of that might be coming from the larger vendors who provide ecosystems and support. So just as an example, think of the App Store. Apple is providing this opportunity for any developer anywhere to put their app on the App Store and make revenue off of it. So the access is really easy and that. But you don't get the same sort of provision with Altera and Xilinx. If you make FPGA IP, they won't put you on their website. Not unless you're making $1 million already. How do you build that credibility? You don't get any support or help from them unless you do more business for them and document how much business you make for them. And so they're treating it like a frequent flyer mile program rather than building an ecosystem kind of a thing. And I think that's the wrong model that needs to be changed around. If you want to have this really successful open source hardware, you need to support the open source community in many ways. And that includes things like promotion and access and doing some of the trivial things that they can do on that end to help it easier for you guys. And at the end of the day, these large vendors are always going to make money on their hard product sales. And so they can spend a little bit on building the ecosystem so they can make even more money back. They don't have to tax directly by charging or taking a commission off of your apps on their app store, for example. But I think that's something that can be done overall and build up a better community. That's all I had to say. Thanks.
All right, so I'm Vaughn Betts from the University of Toronto. I'm going to talk about a different kind of open source hardware, about FPGAs, not about processors. So in the past, my work in this area has been open source FPGA CAD tools. I'm showing here on the right-hand side a complete CAD flow for FPGAs called the VTR CAD flow. It consists of 3 major tools. So Odin 2 does the first stage of synthesis, ABC from Berkeley does the second stage, and then VPR, which is a tool I mostly work on and my collaborators and students work on, does the physical implementation, placement, routing, timing analysis, etc. I guess the unique feature of this tool is that it takes a description of the FPGA architecture. So you can target a wide variety of chips, but it's describing what you want to do. So it's not tied to one chip, so it allows you to explore different ideas. And that's the main thing this has been used for in the past is to research new FPGA architecture ideas. So it's been used extensively for that in academia. It's also been used as a framework to develop new computer-aided design ideas. So you don't have to make everything yourself. You can take your new algorithm or idea and embed it into an open source system, and it's much less work. This tool, so VPR, the tool in the red box there, has kind of a back and forth history with open source. So I wrote the original version during my PhD. It was free for use by researchers, but not for commercialization. And I never actually defined that really precisely, but I put that on the website thinking maybe we'll commercialize this. And myself and some partners did commercialize this. We created a startup because there was a lot of interest from not only academic research, but also companies. So we created a startup to commercialize this, take that open source code, add many features to it so that we could do more extensive architecture explorations, and we could target specific chips, and we worked a lot to refine the algorithms. So that was successful. One of our customers was Altera, which acquired us, so I spent 11 years at Altera. So inside Quartus is a version, the great grandchild of that VPR tool, so enhanced a lot through that experience. And Altera, now Intel's architecture exploration tool, the way they architect their next generation chips is also based on that code base. Okay, so there was a successful commercialization of a partially open system. Okay, so that was the past. What am I doing right now? Well, research is still a big focus of that tool. So that tool flow is alive and well, and actually has more people contributing to it than ever. And its number one purpose is still to research new CAD algorithms, new ideas for FPGA architectures. But something that's been happening over the last probably couple of years in particular, well, it's been growing gradually over the last few years, is completing the stack. So there's a key thing that's missing from that flow I showed on the prior slide, is bitstream generation. Okay, so you get an estimate of how well your design's going to work in a certain chip, but you don't actually get a bitstream. You don't actually program a chip. So multiple FPGA startups, so various commercial companies, have actually taken this VPR code base and added a bitstream generator at the end and used it as their production CAD flow. So inside the tools they ship with their chips, that's what's inside of there. And multiple research projects that have gone all the way to silicon. So there are 3 active DARPA projects that I'm aware of that their chips are all using VPR and that VTR flow that I talked about earlier to program the final chips. But they've added, each of them has added on their own bitstream generator, that final stage of all the decisions are made, now just generate the programming file for the FPGA. As another effort called SymbiFlow, largely driven by Google, where they're programming existing commercial devices. They've picked one of the smaller Lattice devices and one of the Xilinx devices. And that project has reverse engineered part of the bitstream, and they've built their own bitstream generator after VPR so they can, again, go through that CAD flow. They've got a detailed model of the Xilinx and Lattice devices, and they can program. And then the last thing that's gone on to complete the flow is there are actually now multiple layout generators. So you come up with your new idea for some kind of spatial architecture. So maybe it's an FPGA, maybe it's something that's not quite an FPGA, but it's not a processor either. It has the notion of wiring things together programmably, so it's a spatial architecture. You can take that VPR description, the architecture description that's driving these CAD tools, and there are now also multiple layout generators that work in different ways, but usually they will use some standard cell tools to help them complete the design. So they lose some efficiency, but they basically take an architecture that you've described and they can make you a layout, and they'll also make a programming file. Okay, so what this means is we have a lot of different projects that are essentially completing this flow over and over again, creating bitstream generators, some creating layout generators. So we're repeating a lot of effort. And one of the promising things that happened in the last couple of years is these teams are now talking to each other, and we're seeing where can we make one bitstream generator that people use for the future so that we don't all keep reinventing this. So completing the flow. Okay, so future. So the ideal, what I'd really love to see happen with this project is that it becomes an open compiler for FPGAs, so be like GCC. And it has some aspects of that already, but not all of them, because as I said, usually right now, companies that are taking this tool or researchers going all the way to layout are kind of completing the flow themselves by making a bitstream generator. So we want to finish that. What are some of the barriers? Well, one of the things that GCC can do is it can program chips that you just go out and buy, right? So it can program pretty much every processor. And one of the barriers we have is that means you want to program existing commercial chips, not just sort of research chips or unique imagers coming out of MIT and so on. To do that, you need to reverse engineer those commercial bit streams because all of the current FPGA companies have closed bit streams. They don't publish the format. So that's doable, but it's tedious, and it means you're always late to market. You'll never be up to date with the latest chips. I think it's going to be very hard to convince the largest vendors, the Xilinx and Intels, to open the bitstream. The reason is they see their CAD tools as some of their crown jewels. They want people to use those CAD tools. They do not want people to be able to go through other flows with different software licenses. So there are a bunch of reasons that they're reluctant to open up their chips. I think the more likely thing to happen is some of the smaller vendors. So a Lattice, maybe a Microsemi. If there are high quality open source tools and there's momentum there, so the prospect of them getting better, then that gives them some incentive to open up their bit stream. And it's going to be the smaller, hungrier vendors, I think, that are more likely to do that. I talked a bit about how Google's driving some of this effort to make a common assembler. And that is interesting. Why is Google doing that? Google believes strongly, I don't have a perfect answer. I've asked them this, and they won't necessarily tell me everything. I think there are two basic reasons. They strongly believe in open source. Okay, they do not trust things where they can't see the source. That's their philosophy of software. They want it open. It's actually their philosophy as they're moving into hardware. They want it open too. They want to see what's in the hardware. They want to see the tool flow. They don't trust things they can't see and can't change. Their big enough that that has some impact, especially on these smaller vendors when they say that. So maybe we can get this flywheel going, create some pressure and some positive feedback. Another challenge we have is these are very complex tools. So we're talking now not just about open source hardware, but open source CAD flows, which are necessary to make this hardware usable. We have that for processors, but for most other kinds of chips, like FPGAs, where the programming problem is different, we don't have full-featured tools for that. So they're complicated. So we don't actually want everybody just contributing code back because it's very easy to break these tools. It's very easy to degrade their optimization. They're more like sports cars than wagons. So you don't want everybody in the neighborhood coming over and tinkering with their engine on your car while you're out and seeing what happens. But we also need to enable the community to contribute, right? So that we don't wind up reinventing the wheel a lot. So we need more architects and code reviewers. And the challenge is that this project and projects like it are mostly driven by academia. And our students are always graduating. Professors are always busy, so it's hard to have these architects available to mentor new people, to review their code, to architect the system. What can we do to make that better? Could industry or a research consortium fund it? So some of the beneficiaries, maybe these companies with unique spatial architectures that need a CAD flow, some of the smaller FPGA companies, if they fund that consistent effort to have some architects of these tools, then they can really enable them. How can we build a community? How can we mentor people? How can we grow the number of people who can contribute to this? Because a related thing is forking. So, so you're building these complex tools. You're a grad student doing some research. So you take the tools as they exist, you add your new feature to them, you publish your paper. You feel you are done, right? You are not keen to clean up your code, have it reviewed by others, get it back into the code base. So this produces a lot of forking, grabbing a copy of the code, adding your stuff in. Another set of contributors are those who kind of do it for fun, okay? So they're not doing it for research, they just like building things. It's also, you get more immediate results, and in many ways it's more fun if you just grab a code from somewhere or you rewrite everything from scratch, rather than figuring out some complicated code base and having to have code reviews with people seeing, is this going to be maintainable? So there's some natural reasons that we have lots and lots of forks. There are just the VPR tool that I talked about, there are more copies of it floating around that have features added to them in various schools than I can count. But that's redundant work, and it makes for slower progress. If we could get more of that work back in the trunk, in the sort of main version that continues to grow and evolve, we could get more done. How do we incentivize that? How do we organize that work? So part of it is having these architects and reviewers. I'm not sure, I guess it's a tricky one. I think once you get momentum going, like GCC, once that is a very widely used tool, seeing that there's value to putting code back into the trunk of GCC and LLVM. There's some positive feedback cycle here. As a tool is used more and more, people will put more effort to get back onto the trunk. I don't actually have great answers for this beyond that. As an academic community, I think we should try to incentivize research that results in artifacts, not just papers. And if industry valued that will actually help academics value it as well. So thank you.
My past work, so first of all, I'm from Simon Fraser University. I'm in the School of Engineering Science. Besides being head of our computer engineering option, I'm also the NSERC chair for Women in Science and Engineering for the BC Yukon region, which if you're interested in equity, diversity, and inclusion, please look us up. It's wwest.ca, which is just west with an extra W and way easier to remember than that first thing that doesn't fit on a single line of a business card. And it literally doesn't. I've had rather diverse research, so I've tried to focus this conversation a little bit more on the computing things that do tie into this conversation. I've ignored things like reconfigurable microfluidics. So if you have interest of anything weird that's outside of the space, you can talk to me about it. Really the problem I'm interested in is how do you build a heterogeneous computing system? different ISAs, different processor configurations, multi-compute units. And as far as I'm concerned, a nice DCT IP core is just a compute unit that has a really limited ISA. So I've been trying to build something in which we can look at these problems for about 10 years. And I have been stymied on many levels. First work, I managed, ironically, I said up until this point by selling my firstborn, that to get a copy of the Microblaze CPU HDL from Xilinx and created a bootable multi-core soft processor called Polyblaze. Who here's ever tried to bring up a Linux boot? Anybody? I'm sorry, sir. I'm sorry for you as well. Like, the rest of you, if you can avoid it, just don't. I'm on my second time round and it's not fun. The problem with this processor was I couldn't open source it. And so people kept saying, but, well, how can we prove you've really done this stuff? We can't see it. It's an academic question, fair enough. In trying to understand how heterogeneous systems work, I'm interested in how you do performance monitoring for them. So not counters, more than that counters. But we don't have a platform to demonstrate to it, see Polyblaze. And I'm also interested in the APIs and middleware for abstracting, scheduling, and resource management of heterogeneous systems. We did some preliminary work on this. It was called Fuse, Front-End User Framework. It predated the concept of software as a service. I wish I'd thought of that tagline because then maybe somebody would have cited me. But it's just the basic idea that everything is a compute unit. Anybody can pull in those types of resources. So what are we working on currently? So this is what Taiga looks like. Or I should take it back. This is what I want Taiga to look like. Because if I want to be able to look at heterogeneous systems, I want to be able to do any of that. I want to be able to pull up and pull out and rip out the execution phase and do whatever I want to any of those pieces and make it work. What Taiga is, besides a biome in Canada, shout out to Canada, is it was the first soft processor that allowed you to have a variable length execution unit. So within your fetch, decode, execute phase, all the execution units can execute and have different delay slots. And why that's important is that means we can do things like early commits, which helps pump up our IPC a lot. So for example, we looked at how you might change your divider if you weren't actually relegated to 32 cycles to finish a divide. And it turns out that you can use a quick div algorithm that averages 2.5, actually less than 2.5 cycles to complete division on 32 bits, which is a whole lot faster than 32 cycles. It costs you a little bit of space. So if you're going to do lots of divides, then it's actually really worth it because you can get about a 2% performance increase. And this is on the MBench benchmarks. On some of the really high-end ones like simultaneous linear equations for linear decomposition. IPC goes way, way up because you're able to commit out of order and you're able to push in as many operations as you need at any point. And we've been doing some new designs actually that we've even increased our IPC by up to 25%, which will be a future research paper. But really what we were interested in was it's also going to be open source, but I'm not saying how until I publish the paper. Or at least get it submitted. What is interesting is I'm not trying to make money off of this. It doesn't really do me a lot of good, but I could use people with money and bodies to help me make this more usable. So I've been working with the Litex group because you would think, having brought up Linux before, I would either have walked away and said, this is crazy, don't ever do it again, or it can't be that bad the second time round. And neither of those statements are true. glibc, anybody heard of it? So it turns out the time is ending if you're a 32-bit processor in 2038, in case you didn't know that. And glibc hasn't figured out how to fix this yet. They've recognized this is a problem. So now the RISC-V Foundation has chosen to really not move forward too much on this stuff because, well, we want to see how glibc handles that. You can imagine as a researcher how frustrating that might be. I don't want to have to wait anywhere near 2038 to get a copy of the Linux kernel working. So luckily the people in the LITEX group are interested in working with us. I'm bringing that up. Why do I think the platform we've offered is really useful? Well, it's completely open source, so if somebody wants to use it and sell it, they can. If you were really interested in how you're going to do heterogeneous systems, this is a space in which you can do that. Like Guy, ours is actually in HDL, it's in System Verilog, but it's not in Chisel, it's not in BlueSpec. It's optimized to run really well on FPGAs, so it's not massive. Rocket is a fantastic design in Chisel, but it's also aimed at ASICs. So if you're going to play on an FPGA, you might not want to use that. And ironically, I didn't think to put our GitHub up here. So if anybody's interested, feel free to ask me, what do we need? And I've kind of pulled a few things. Help with verification. I really do care if this thing works, because pulling up Linux on a processor that doesn't really work. I mean, you're talking about millions of lines of code. If you want to try and boot something that you think may or may not work, try and bring up a Linux kernel. You'll know very fast whether your processor really works. It would be really nice to not have to try and use Linux to debug a processor, because the error messages in Linux include things like, my kernel is panicking. Don't know what I'm going to do with that phrase. Somebody had a really good sense of humor, but there's absolutely no useful error debugging information coming out of Linux, and I don't see it changing because Linux has been around a long time, and there's a lot of people with a good sense of humor not trying to bring up new Linux kernels. So compliance tests would be awesome. RISC-V has some, not nearly enough. I know they're working on it. But just in anything, an IP core, if you're going to design a function, set up compliance tests for people who are going to use it and adapt it to do other things so that they know the functionality is maintained. More benchmarks that don't need Linux. There's actually very few benchmarks out there that don't rely on being put on top of an operating system, or they're really, really tiny. So if you want to stress hardware, you're having to make up micro benchmarks, which isn't really going to do what you want. Environment support. We don't get money for engineering work. It takes a lot of effort, a lot of engineering work to build a lot of new things, but none of us are going to get money for that. So if you can help us with the engineering work, like Guy gave a good example, porting. The first core gets me maybe some research dollars. The port to the other core vendors does not, even if I really want to. Vaughn made some of the same points. Other tools. So GCC-like flow would be awesome. Realistically, I really want LLVM support. This has been something that's been working with RISC-V for a very long time. It's still not there. But if you're going to do a heterogeneous system design, you want LLVM. You don't want GCC. I'm sorry. GCC is not bad. It's just not really good for putting in heterogeneous descriptors. I'm looking at the idea that we need to fundamentally change the way we view the compilation process. We should not be trying to compile one monolithic thing into one monolithic thing. Realistically, we don't run single application workloads anymore, almost never. So we should be trying to compile a pile of stuff into not monolithic things that can be mapped onto whatever resources we're going to have, and we shouldn't have to know them up front. Easy wrappers for integration and use, that's what I was talking about. And honestly, the biggest thing I think I can add that we haven't talked about before is that you can give us credit. And I don't just mean testimonials, I mean recognition on your website, things we can actually pull when we write our grants. Because one of the things that we have to talk about is what our significant contributions are. And being able to say that there are any vendors or companies who are using what we're doing gives credence to the fact we didn't just create a new widget that is sitting in a corner gathering dust that people never, ever, ever plan to look at ever again. We can't guarantee correctness. We don't have the bandwidth or the manpower to do that. So CPUs, anything of high complexity, anything you can do to help, whether it's formal methods, any kind of verification framework, any kind of access to better simulation, that's where it's going to be better for us. So thank you.
Okay, so I guess we'll now turn it over to the audience for any questions for the panelists. Yes?
I have two things. One is, can we talk about the LLVM? Because as far as I'm concerned, the LLVM is in a pretty good state. You can build FreeBSD with it, the whole thing. So that's a problem that we'd like to know about. I'm more interested in one events. You were talking about the desire for an open FPGA design. Have you looked at the Clifford Wolf's work with the OSIS toolflow, which actually goes for the lattice FPGAs that you mentioned as like the prompt?
Yeah, I've looked at it, and we had some meetings with them. I mean, it's a different effort. It's we'll see how it goes. So far, it's targeting very small FPGAs and gets very poor performance. Okay, so the routing algorithm is pretty basic right now. So it's kind of growing from the reverse engineering, because he's involved in that SymbiFlow reverse engineering. So he's reverse engineering with help from Google and others, the bitstream flow, and he's building a place and route tool to target commercial FPGAs. I mean, he may give a different answer. From a quick look at the architecture, I look at it because one of their engineers basically said, I took the VPR placement engine and put it in and it works way better. And so I went, why are you forking this? So I went and looked at the code. I have concerns about whether it will age well. It's pretty hard coded right now. So, and I may be wrong, but basically I think this is one of the things you have to be careful about. Basically, it's not that hard to write a simple CAD tool for one chip. It's not trivial. But if you want to have lasting impact, you need to get data abstraction so you can target it at different chips, and it has to scale to big ones. And I think if we kind of go the path of you can write a tool quickly by hard coding, it's not going to age very well. So that project may prove me wrong. But based on my experience in both academia and industry, my look at their architecture was that it's pretty hard coded. I think it's fun. It's basically a lot easier to write a cool tool from scratch, but it does divide the effort that's going into things. I guess the good news is all the reverse engineering of the commercial bitstream is completely portable, right? So various people have collaborated to reverse engineer the Xilinx and Lattice bitstreams, and then that goes into whatever tool flow you want. I don't know, does that answer your question or not? I guess it's mixed in with a bunch of personal opinions.
It does. I'd be very cautious. You want to build up a community.
Yeah.
I'd start with the one that's out there and has got, albeit in Western Europe, a fairly good strand. Now, it has a number of goals, particularly around the whole form stuff, which is what I'm supposed to but I would be careful of saying, oh, well, I want a community. There is one out there, albeit small. I would prefer to see that one nurtured.
Oh, I totally agree.
And take it off.
Yeah.
Oh, it's not good enough. Oh, there's no community out there.
No, well, so I actually agree, but I mean, I guess it's there are two relatively independent development efforts going on then to target commercial FPGAs. So VPR is basically, this has mostly been done by Google. They just basically talk to some of the developers about what do they need. They can take the generic algorithms in the open source code, and within a generic assembler that they've written, they can target commercial FPGAs. Clifford's group has gone a different path of they're building an entirely new tool. So I'm not trying to denigrate their work, but I say that there is a cost to that. There may be a benefit of, well, what if you basically just come up with a better solution? But there's a cost of that has split actually the development effort. And I guess I'm not saying that, like, I guess I didn't choose to split that development effort, right? That would be an example where some of the algorithms have actually been ported from VPR into that code base to enhance it because the first placement engine wasn't working well, so now onto their second one. And I think that we'd be better served if we tried to make a tool that is more generic that can be used for multiple purposes, which already exists. So that, I guess that's my perspective on that. harder in many ways, because if you say, well, this tool will only do the following one thing, then that is easier to keep in mind what are my goals. So we'll see. Does that answer your question?
Useful conversation.
Okay.
Do you want to make any more comment on LLVM? Or
I will talk to him offline.
Okay.
I mean, in a good way. Anybody who wants to make my GCC problems go away.
Any
If
other-
you want to solve my Linux problems, just, well, this
Give her
seems to
the
be a good
microphone.
day. Since this seems to be a good day for me, if LLVM problems solve my GCC problems, anybody want to solve my Linux problems? No? Okay, just thought I'd check.
Any other questions? Yep.
Hi, my name is Martin. I guess one of the things I've observed in the software world is if I develop a Java application, doesn't matter where I work or what project I'm working on, I have a well-defined ecosystem and a well-defined flow. That's easy in software because you only compile to one target. In hardware, everybody writes their own make file and then you try to integrate multiple things together. It's a nightmare of integration each time. I spend more time integrating stuff than writing actual production code. Is this something you've seen as well? And what are your thoughts about it?
So I guess it's almost 10 years ago, the ITS came out with the Silicon Roadmap. Sorry, can't hear me? ITS came out with the Silicon Roadmap in which they said people spend 30 to 50% of their time on integration, 50 to 70% of their time on testing and debugging and verification, and 10% of their time on design. And no, that number does not add up to 10 or 100%. I'm very aware of that. But yeah, 30 to 50% of your time on integration. So I 100% believe what you're saying. It's a ridiculously crazy problem because it's not just that the IP is to work in your make files, it's what operating system are you booting, with what version of the tools are you running, with what libraries and package. It really is a crazy problem. I feel your pain. That was part of one of my last points was ease of use and integration. So I think it's something to be tackled. I really do, because even if my core or Guy's core or any of these gentlemen's cores are extremely well written, the packaging to make it accessible and usable to the broader space is again something we will get no money for from research, but is something that we need to make cores work. Software packaging becomes a lot easier because you basically just have to have one OS or the other, or maybe if you're lucky, both. So I think it's a huge pain point. I think we need help with it.
Anybody else?
Yeah, I also agree 100%. We may take more time integrating than developing. And I think at that place, open source has a role to play, because if we're talking research, we don't need the latest technology, we don't need the most performing, we don't need high volume. So we could have an open source ecosystem, place and route. This is for FPGA, but could exist for ASIC as well. That can be generic enough, fast enough, but that produce something that is not maybe the best. I don't care. If it takes less time to design, we could use it, because we spend so much time doing that, which has no value in terms of research. When we for a given paper, a given ID, we spend so much time learning, because when we start, we learn, then we design and integrating, and the time spent to do that is nothing compared to just the small ID we had and that we put in the paper. If we compare with researchers in software, that's way more easier for them. They just have the ID, they implement it. It's easier, way more easier. So I think open source tools for hardware can help with that. At the end, I don't know what you think, but yeah.
Not sure what you mean by integration, but I know in the FPGA side of things, we spend a lot of time with something simple like just bringing up a new FPGA board. So to get our processor system onto that FPGA board and working, we've done this dozens of times with dozens of boards and we've worked with every single vendor's CAD tools. So I have professional employees doing this. And we just got a new Stratix 10 board and we spent 2 weeks trying to bring up our system and it still doesn't work. Just board bring up. So we could do a better job, I think, on making these things easier to use. You might call that part of the integration effort of just bringing up the board so that you can start doing more coding and whatever. But there's still challenges with just bringing up boards, and it's a standard board offered by Intel. So I'm not trying to say that there's a problem with our board or anything like that, but there are challenges that we run into problems all across the board. And just as an example, the simplest problem that we had was we're trying to run the latest version of Quartus Prime, but we couldn't get it to work because it didn't recognize the license manager. We had an older version of FlexLM running, and it should have checked out the license fine, but it didn't. And so we had to upgrade the license manager on the server, and that cost us half a day, just as an example.
And here I was going to say that the tools had actually gotten better. I was thinking back to 2000, I had to install the major vendor FPGA tools, and one of them took me 3 days to get up and running for the lab to use. So we've gotten slightly better. That doesn't normally happen anymore.
I can give a couple of examples. For example, if I do something in Java, I look at the Java directory structure. It's the same across every single Java project. So writing a build tool on top of that is trivial. They've done it with Maven, Gradle, and in the past, Ant and Ivy. So if I look at Python, well, Python has had a rocky ride where they didn't care too much about their packaging, and then they created a bunch of tools, setup tools, and now they're up to something called Poetry. They're still struggling, but it's getting to a point where they're going to have a unified way of developing Python applications. If I look at C, well, it's a bit of a mess there, but pretty much everybody agrees that they should use auto tools and make files more or less the same way across every project, or CMake. When I look at hardware, every single person thinks they want their project to be different than the next person. And they just create whatever random directory structure they feel like that day. And no one can come up with a build tool that's going to be able to build any hardware project because there's nothing common.
And that's what I mean by system build tools that we need as part of an ecosystem. We need a multi-vendor approach that allows you to create these hardware applications. And then you can use Quartus as a backend or Vivado as a backend or any other vendor tools as a backend. But you need a system build tool which is consistent and works with all of those environments and allows you to set up your projects in a very specific way so that things are portable and testable and validated and so on.
I'm going to play the devil's advocate and just be nice to the vendors for a moment. One of the reasons all this is so much easier in software is we gave up performance decades ago. We said we want abstraction, we want it to be easy, so I don't care how fast it runs. We're going to make the people who build the hardware make the software run faster for us. That's effectively what we did. Now, I am totally in line with the idea of having some sort of universal design flow, but we've got a bunch of vendors who made their money by making it possible for you to build the fastest thing possible, because why did you go to hardware? You needed it to be faster. So now we're saying to them, we don't care anymore about faster, but well, we do, but I mean, you're going to give up some faster. Well, you're going to give some faster if you want to have something universal to do build. And in terms of a generic way of doing things, big companies do have them. Like if you are inside Philips Semiconductors or GM or GE and they're building widgets, Samsung, internally within those companies, absolutely very rigid design parameters, very rigid structures. Okay, maybe they've gotten rid of them in the last 5 years, but they used to have them. There were rules for check-ins, checkouts, validation, because that's how they create IP that they can reuse and port internally. But
Doesn't help the open source community because those are proprietary workflows.
I 100% agree on that. And you can at least get the workflows, hypothetically, if you want to get every single equivalent to software engineering course to use some sort of flow, and then we can maybe turn out generations worth of students doing some structural flow that all looks the same. You might get somewhere, but I teach one class, Guy teaches another, Vaughn teaches another. Some of it's by experience. We might be teaching slightly different flows, which means our students come out thinking this is a slightly different better way to do it. There's not a holy grail textbook that's really good at this. So I'm just saying that you have a completely valid complaint. I just know how we got here and it's not an easy place to get out of. Yes. Okay, observation. I could complain about those, so it's okay.
Thank you.
Probably easier so people can hear me. I just pick up on that issue of speed. You do make a trade-off. If you want it all to be super easy, you're going to carry performance penalty. And on the whole, you don't write weather forecasting optimization algorithm in Java for exactly that reason. But I don't think you're going to persuade the chip companies to go away from trying to make things go fast. Look at the Apple product announcement last week. When you have the head of engineering coming onto a public forum and talking about the number of clock domains, the number of voltage domains, and it's not a speed thing, it's an energy thing. And it matters for Apple because how long before your battery goes flat when you're running things? It increasingly matters for deep learning applications and inference at the edge. And actually, if you stand back and then look at Google and Amazon, between them, they spend about $1 billion on electricity each year. They're not going to go anywhere down encouraging chip manufacturers to do anything other than the most super energy efficient. Okay? Think what a 5% energy does to their stock price.
Make a comment? One more question? Okay, I guess, Rick, you want to wrap up? Well, thanks a lot for the panel and presentations and questions.
It's okay, you can leave them there. It's okay. All right. Well, it's kind of a sad moment, isn't it? Just going to make a couple of observations as we close. Going to put this guy up so that you remember to set these dates aside. They may change, but plan on participating a year from now. Like I said, we're going to check attendance, make sure we have perfect attendance from everyone. Who all here, I'm sure everyone here has heard of Red Hat, right? A very understandable business, built on open source operating systems. To Guy's point, a services business as opposed to an IP or a licensing business. And IBM's largest acquisition ever, right? $34 billion acquisition for Red Hat, right, when they bought the company. So understanding how to leverage open source artifacts and build a business around open source technology in the hardware space is new, for sure. Something that we clearly need to learn how to do together. But there's no doubt that having these open source artifacts upon which we can continue to innovate and build other value, even if it's just other IP or other services businesses, is, there's existence proof in the model. We just need to figure out what that means for the hardware space and make it easy, right? So that tear your hair out every time you try to configure a new system. So thanks very much to all of our sponsors for helping us put this together. I hope you enjoyed the day. Please provide feedback to me or any of the other people that you met. If you enjoyed it, tell everybody. If you didn't, tell no one. No, honestly, we really appreciate you spending your day with us, and hopefully you enjoyed it, and we'll see you next year. Thanks very much, everyone.